Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to our presentation on the automatic basketball scoreboard system, a project built at the exciting intersection of advanced athletic computing, electrical design, and mechanical engineering. Sports are fast, dynamic, and rapidly evolving. Today, tracking scores accurately and instantly is vital for both casual players and professionals. However, traditional scoring relies heavily on human operators or complex, expensive optical setups. Our goal was to design, model, and simulate a highly robust mechatronic scoreboard system capable of automatic detecting successful baskets and updating a digital display in real time. Over the next few minutes, we will walk you through the electronic, logical, and structural journey of bringing this smart sports system to life. To give you an idea of how we structured this engineering journey, let's take a look at our project roadmap. Our engineering process was divided into 6 core phases to ensure that both the electronics and the mechanical housing worked in perfect harmony. First, we'll cover the high-level system overview of how the automatic scoreboard functions. Second, we will introduce our software toolkit, the digital suite that made this design possible. Third, we'll dive deep into the digital logic brain of the system. Fourth, we will look at our hardware PCB layout, specifically focusing on our unique U-shaped circuit board. Fifth, we will transition to the mechanical design of our heavy-duty basketball rim. And finally, we will share the engineering challenges we overcame and the invaluable lessons we learned throughout this cross-disciplinary collaboration. Let's start with the big picture. How does the system actually function on the court? At its heart, this is a mechatronic system. It bridges the gap between physical motion and digital data. When a basketball passes through the hoop, it triggers a physical sensor. This sensor instantly generates an electronic pulse. This signal is processed by our custom-designed circuitry, which immediately updates the score on a high-visibility digital display. To make this happen, we focused on 3 pillars. Circuit design, using OrCAD to design robust sensing and signal conditioning paths to accurately track the ball without false triggers. Mechanical modeling, using Autodesk Inventor to build the hardware housing, ensuring that our electronics are safely integrated directly onto the rim assembly. Lifelong learning, adapting to new design, tools, and industry standards to refine our engineering skills. Of course, none of this would be possible without the right engineering software. Let's look at the toolkit we used. To bridge the gap between electrical and mechanical engineering, a workflow we call E2M, or electronics to mechanics, we relied heavily on 3 industry-standard tools. First, we used OrCAD Capture and PSpice. This was the drafting board for our system's logic brain. PSpice allowed us to run digital logic simulations, ensuring our counters and decoders would function perfectly under real-world timing conditions before we built anything physical. Second, we used OrCAD PCB Editor. Once our schematic was simulated and approved, we used this tool to lay out the traces, organize components, and wrote the connections on a physical board layout. Finally, we used Autodesk Inventor for mechanical design. We modeled the physical rim, the backboard, and the custom protective enclosure. This ensured that our U-shaped PCB would fit snugly inside the mechatronic assembly without mechanical interference. Now, let's take a closer look at the actual electronic brain we simulated in PSpice. Instead of using a complex, expensive microprocessor that could fail or suffer from software bugs, we opted for a highly reliable hardware-level digital logic circuit. This architecture is broken down into four key stages. The input stage. When the basketball passes through the hoop, the sensor detects it and generates a clean, debounced electronic pulse. The counter stage. This pulse is fed directly into a 7490 decade counter chip. This chip counts the incoming pulses from 0 to 9 and outputs the current tally as a 4-bit binary coded decimal, or BCD signal. The decoder stage. A raw BCD signal can't be read by humans, so we pass it to a 7447 decoder chip. This chip translates the 4-bit BCD code into individual segment activation instructions. The display stage. Finally, these instructions illuminate the correct LEDs on a standard 7-segment display, showing the score clearly from 0 to 9. This pure hardware logic is incredibly fast, cheap to manufacture, and highly resistant to software crashes. Once the schematic was finalized, we had to translate it onto a physical circuit board that could live on a basketball hoop. A standard rectangular circuit board simply wouldn't work for this application. It would either block the hoop or stick out, making it an easy target for a stray basketball or a player's hand. To solve this, we designed a custom U-shaped PCB. This unique geometry allows the circuit board to wrap closely around the neck of the hoop, tucking safely away inside a protective enclosure. Our board features a robust layer architecture. Copper layers. We routed high-speed logic signals on the top layer and used a solid ground plane on the bottom layer to eliminate electrical noise and interference. Solder mask. We added a protective coating to prevent electrical shorts and shield the traces from outdoor moisture. Silkscreen. We printed clear components labels like U1 and R1 to guarantee an accurate, error-free assembly process. With the electronics sorted, we needed to make sure the mechanical structure supporting it was equally robust. Basketball is a highly physical sport. The rim must withstand intense vibrations, heavy ball impacts, and environmental wear. Using Autodesk Inventor, we built a fully parametric 3D model of the rim assembly. We selected carbon steel for the hoop itself, giving it the yield strength required to handle heavy shots without bending or warping. For the backplate, we designed a high-density polycarbonate mount. This provides a highly rigid support structure while remaining lightweight. By modeling the entire system in 3D CAD first, we were able to run stress simulations to verify that the metal hoop wouldn't deform, protecting our sensitive electronics mounted just inches away. However, bringing electrical and mechanical designs together always reveals unexpected hurdles. Let's discuss how we solved them. In theory, everything works perfectly. In practice, we faced three major engineering roadblocks. First, impact vibrations. Every time a ball hits the rim, it sends massive shockwaves through the assembly that could easily crack solder joints on our PCB. To solve this, we integrated shock-absorbing rubber bushings at the mounting joints, dampening the physical vibrations before they reach the electronics. Second, crowded wires. Because of our compact U-shaped board, routing all the logic signals got incredibly tight. We resolved this by implementing multi-layer routing, dividing our signals across different layers of the board to prevent overlapping or short circuits. Third, board and box mismatch. Initially, there was a minor size discrepancy between our electrical CAD design and our mechanical enclosure, which risked physical collisions. We resolved this by exporting a precise 3D step model for our PCB from OrCAD. directly into Autodesk Inventor, allowing us to tweak the enclosure for a guaranteed 100% accurate fit. These challenges pushed us to think outside our comfort zones, leading to some incredible learning experiences. This project was more than just an engineering exercise, it was a masterclass in cross-disciplinary collaboration. As team leader, I learned the immense value of establishing a seamless bidirectional data flow between electrical and mechanical software. Real-world engineering requires these departments to speak the same language. Our electronic designer mastered hardware-level piece-by simulation, proving that digital testing saves significant time and manufacturing costs by catching circuits issues before printing a physical board. Our mechanical designer utilized advanced interfering checking in Inventor, proving that digital prototyping prevents costly manufacturing mistakes. Ultimately, this project demonstrated that electrical and mechanical engineering must work as one cohesive unit to create successful, robust, and smart physical products. That's all from us. Thank you.